When most of us hear the word carbohydrates, we immediately think of one thing: energy. Bread, pasta, fuel for the day. But today, we're diving into the absolute dynamic and complex chemical world of carbs. Because trust me, they are far more intricate and fascinating than just a quick sugar rush.
We're going to break down their essential chemistry, starting literally at the microscopic, fundamental level, and then building all the way up to their tangible, macroscopic impact on our daily lives. So are they just fuel, or is there an entire hidden chemical universe inside them just waiting to be unlocked? Let's dive right in and find out.
All right, Section 1, Monosaccharide Reactions, the fundamental building blocks.
Let's kick things off by looking at how a single sugar molecule actually behaves when we tinker with it. If we use a catalyst, like hydrogen and nickel under high pressure, D-glucose gets neatly reduced into the sugar alcohol sorbitol. Simple enough, right? But watch D-fructose. When we reduce fructose, it yields both sorbitol and mannitol. You might be wondering why the difference. Well, it's because this reaction creates a brand new chiral center, basically a completely new point of 3D structural asymmetry right at the second carbon.
Now let's flip it around. If we oxidize these simple sugars, the aldoses, we can actually get 3 completely distinct sugar acids, and it depends entirely on exactly which site you target. It's like a molecular puzzle. Oxidize just the C1 aldehyde, you get gluconic acid. Target only the C6 primary alcohol instead, boom, you produce glucuronic acid. And if you go all out and oxidize both at the exact same time, you create glucuric acid. I mean, that is some serious molecular precision in action.
Moving right along to Section 2, Identification and Rearrangements, what I like to call shape-shifting sugars.
So how do chemists actually spot these tiny molecules in the lab? Well, look at the reaction of the carbonyl group. Here, glucose reacts with excess phenylhydrazine in a heated 2-step process to form D-glucosone. And what's cool is this creates a very characteristic yellow crystalline compound. Chemists actually use these distinct crystals, and specifically their exact melting points, as a sort of molecular fingerprint to positively identify the sugars.
But here's the thing. Sugars are not static. They are incredibly adaptable. In weak alkaline solutions at low temperatures, glucose pulls off this amazing molecular shape-shifting trick. By passing through this temporary chemical stepping stone called an enediol intermediate, it undergoes a really complex rearrangement. This literally allows the molecule to freely interconvert between glucose, fructose, and mannose. They just flip between identities like it's nothing.
Okay, Section 3, the power of polysaccharides, starch, glycogen, and cellulose.
What happens when we take those shapeshifters and link thousands of them together? We get 3 main polysaccharides: cellulose, starch, and glycogen. Now what's wild is they are all built from the exact same fundamental unit, glucose. But notice how the unique linkages, like, alpha versus beta bonds, and their varying degrees of branching dictate totally different shapes and biological roles.
Let's focus on starch first, since it's our primary dietary energy source. Notice how it actually combines 2 different structures. First, you have the unbranched amylose coils, which are connected by alpha-1,4 bonds. But then you also have amylopectin. Amylopectin introduces alpha-1,6 branch points, creating this much more complex branched network that can make up to 80% of the starch. Now, glycogen takes that branching and just pushes it to the absolute extreme. We find this mostly in our liver and muscle tissues. This animal starch creates a highly compact, almost tree-like structure, throwing out branches every 8 to 12 residues. And why does this matter? Well, this extreme branching exposes a ton of non-reducing ends, making it super accessible for the enzyme glycogen phosphorylase to rapidly harvest energy the second your body needs it. And finally, we have cellulose. This is literally the most abundant organic substance in the world. But unlike starch or glycogen, cellulose relies on straight-chain beta-1,4 linkages to create incredibly tough fibrils. Here's the catch for us, though. Humans completely lack the cellulase enzymes required to break those specific beta linkages, which is exactly why we can't digest wood and why cellulose acts as our essential dietary fiber instead. It just passes right through.
Let's wrap up with Section 4, Pharmaceutical Applications and their real-world impact.
So how does all this microscopic chemistry translate into the real world? Well, in the pharmaceutical industry, these precise chemical properties are absolutely critical. Carbohydrates serve as everything from basic diluents and binders in your everyday tablets, using stuff like lactose and starch, to providing sterile IV dextrose for patients in the hospital. They even function as vital cardiovascular therapeutics, like the widely used antithrombotic drug heparin. It's way more than just food.
From basic energy storage to complex life-saving therapeutics, carbohydrate chemistry is truly the invisible architect of our health. It really leaves us to wonder, knowing what you know now about oxidation, chiral centers, and structural bonds, what other molecular secrets are waiting to be uncovered in our daily lives, hidden right inside your next meal or medication?